Hello, welcome everybody to our webinar today about automated overland oil spills modeling from pipelines using OilFlow2D. My name is Reynaldo Garcia. I'm the Director of Development and Applications at Hydronia, and I'm going to be sharing with you today our latest developments on these new tools. I want to make sure you can hear me well. And if you can, I will appreciate if you can drop me a quick line on the question panels or the chat panel, whatever of those work for you. And we'll get started quickly. Okay. Okay, it seems you can hear me well. Okay. Well, so today's webinar is about optimization of the Overland oil spill tools that we have in OilFlow2D. So the first part will quickly deal with an overview of the OilFlow2D system. Then we'll describe the oil pipeline tool, and we'll mainly focus on the automated batch processing for modeling oil spills. That's the main topic of today's presentation. I want to first thank the users who made possible all this development. As you know, we are very active in developing new tools all the time, and most of the things that we develop for the model are based on requests from our users. And we continue to do that all the time, and that is possible for the support that you give us by getting licenses and maintenance for our models. So the pipeline tool and the OilFlow2D model can help the users to simulate different kinds of oil spills. And one of them is the spills originating from pipeline leaks. They can occur in different ways, in different locations, but most of the time, the applications deal with analyzing a large amount of spills that can occur potentially in pipelines. So you want to analyze the risk that is involved in potential spills, and that require for long pipelines many spills. And what we are trying to do is to optimize as much as we can the process of simulating this kind of spills. So the main purpose of modeling oil spills on land and water is to determine the affected area caused by crude oil spills. So what is the affected area, where the oil is going, when it is arriving to the different locations. And the main purpose of that is to assess if the oil is going to hit high consequence areas, what is called HCA. That can be urban areas, sensitive ecosystem, streams, water bodies, water supply systems, and so forth. The origin of the spills can be of different sources, well blowouts, pipeline, tanks, and in the case of water spills can be originating from tankers or ports or different locations that are near water bodies. Now, the OilFlow2D system, it's basically a software. It's a modeling system that can account for spills in land or overland, what we call the overland flow model, and also on water. So the main system consists of a two-dimensional oil and viscous fluid hydrodynamic model that is based on with numerical aspects can utilize flexible mesh. And I will talk a little bit about this later. And it's optimized to run in GPU or CPUs in parallel mode. So it takes advantage of the multiple processors that the CPU or the GPU, the graphic processing units, provides. And this helps the model to run much faster than it would if it would run in a single core or single processor system. It can deal with point sources, rainfall evaporation and infiltration. And you may say, well, rainfall evaporation, why would the oil flow model would deal with rainfall? Because the OilFlow2D model includes a water flow model that can be used for the oil and water spill model, and that rainfall sometimes is important in those simulations for the water flow. Then it can handle also hydraulic structures such as bridges, weirs, gates, culverts, and it also can consider the effect of wind on the water surface or the oil surface. Now, the Overland component or the Overland model, it can consider evaporation of the oil based on the oil characteristics, infiltration of the oil into the soil as a loss, hydraulic structures as well, heat transfer with the environment. And when I mentioned heat transfer, the model can consider how the oil interacts with the environment in terms of the transfer of energy, of heat energy between the oil and the environment. And this is important because that effect can generate variations in the properties of the oil, such as the density and viscosity, and in turn that can affect how far the oil will travel from the spill original location. So for certain oils, this is very important, particularly those who have a high pour point. So the fluid properties can vary with temperature, and the oil pipeline module can particularly deal with the oil within the pipeline and consider the pressure and the hydraulics within the oil pipeline to determine the outflow from different points that the pipeline can break. Now, the oil and water spill model can simulate the trajectory of the oil by particle tracking, and also deals with evaporation, emulsification, dissolution, and shore interaction. And we recently added two new components to this model, which is the containment booms and oil spills from moving ships. The flexible mesh that we use for the numerical computation is a mesh that is formed by triangles. It's automatically generated in the model, and the triangle is the main computational unit. And within the triangle, the model computes the velocity, the depth of the oil, and other parameters that are important in the process of simulation. This is an example of the model applied to simulate a tank spill. There is originally a tank over here that contains oil. The tank burst, and then the oil starts flowing on this urban area through the streets. And this color represents the oil thickness or oil depth along the simulation. And the two different animations here, the right is the same tank, but solved for a condition where the wind speed would be 20 meters per second, while here will be 2 meters per second, which changes the heat transfer considerably. And for this particular oil, how the simulation represents the stopping of the oil due to the spill transfer, heat transfer here. So you can see here that it's much farther away that the oil travels in these conditions. And in these conditions, the oil stops relatively close to the tank because of the increase in viscosity of the oil due to the high wind speed that increases the heat transfer with the environment that is much cooler than the temperature originally in the oil here. This is another animation of a water spill, including booms. There are 2 booms here in this river, and this booms has a 50% catchment capacity. This is 100%, and as you can see here, the oil can't. The booms can contain this part of the oil here, and this the rest of it is further downstream. Now, the oil spill modeling from pipelines has several challenges. One of them is the requirement that usually these simulations involve is to run hundreds or thousands of scenarios for long pipelines. So you have to run one spill every, let's say 10 meters or 20 meters or something like that. And for a long pipeline, you can imagine the amount of spills that this will involve. Typically, hundreds or sometimes thousands of them. Also, they require calculation of the potential spill volumes from each spill. So based on the initial condition within the pipe, we need to estimate how the volume that is spilled from here. This is not only a single volume, but how that volume is spilled in time. So it's a hydrograph that represents the volume per unit time that can be spilled from a given location. Then once the oil hits the terrain surface is not flat. It's very complex sometimes. It may have vegetation. It may have different topography, and rarely the flow paths are one-dimensional. The viscous flow with a free surface is a real need, so it's not sufficient to consider the oil as a non-viscous or low viscosity fluid, because the viscosity plays a big role in how these fluids behave on the terrain surface and also on the water surface. Also, oils may be non-Newtonian. That means that the viscosity may change in time and also with the speed of the fluid, and the properties may change also during the spills. Each spill simulation can potentially generate huge amount of results based on the model output, and this should be processed to create maps that represents the affected areas, the depth of flow, the arrival times, and so forth. So quite a number of challenges there. Now, the oil pipeline module of the OilFlow2D allows automating the process of simulation of these hundreds or thousands of leaks from a pipeline. They can integrate with the Overland and the oil spills on water models. So it's a integrated approach that you can use. You can use it as a standalone, but you can use it also integrated with the Overland flow model. Now, the oil pipeline module includes 2 parts. One is the pre-processing, and the second part is the post-processing. The pre-processing is the one that is used to compute the outflow from the pipeline at multiple spill points. And it automates the creation of the sources layer that is necessary for the batch processing of the overland oil spills. So the model computes the sources location, and at each source location, it computes initially the steady state initial pressure distribution along the pipeline that is necessary to determine the outflow from each leak location. It can consider the closing time of the block valves that can be in the pipeline to limit the once the leak is detected. They're usually block valves that are closed very quickly in order to close the areas that are subject to these leaks and minimize the amount of oil that is getting out of the pipeline. The outflow rates are calculated for any diameter, user-defined diameter, in two stages. The first stage is the period between the initial time, so the initial conditions in the pipeline, and the valve closing, and then the period with between the closing of the valves and the final oil drainage from the pipeline during the depressurization. The pipeline polyline can contain elevations, or the program can assign the elevation based on the digital terrain model that you are using for the overland flow. Now, it's important to remark that the computation of the outflow is based on the hydraulics. It's not just a volumetric computation that can lead to very different outflow estimates. So this is actually the hydraulic computation that is determining how much volume and how long does it take for the drainage of each particular spill location. The second part of the oil pipeline module is the post-processing that includes the numeric provides the numeric output for each spill point. That includes the outflow hydrograph. That means the oil flow rate or discharge versus time, the total oil volume drain from upstream and downstream from the spill point, the oil volume drain from upstream after and before the valve closure, the volume drain from upstream and downstream. I mentioned this already after the valve closure. So you get a lot of information about how the drain down of the spill occurred. You get also the pressure head along the pipeline for the initial conditions, the general tables for hydrograph for all spills that are used not only by the model itself, but also to prepare graphs in Excel, for instance. You can generate maps to represent the affected area, the arrival time, the depth of the fluid at different times, and the maximum values that are obtained during the computation. There are different type of maps that indicate these parameters, and all are stamped with the ID of each spill. And you can also get integrated maps that includes all of the spills along the pipeline. Now, the application workflow for the use of the oil pipeline module includes the use of the QGIS, which is the basic software that we use to pre-processing and post-processing. And in this QGIS system, we have developed the plugin that is the one that computes all of the variables in the oil pipeline module. For that, you need to create a new OilFlow2D project, load the terrain elevations in the form of a digital elevation model. It can be a raster, for instance. You then can create the oil pipeline and valves layers. The oil pipeline is the layer that contains the oil pipeline itself. It's a polyline, and the valves is a layer that contains the block valves that are or can be along that pipeline. Then you enter the pipeline in this layer and the valve locations in the valves layer, and run the program to calculate the flow rate versus time outflow from each of the spill, and also the program will compute and generate the sources layer for you. So this is a general workflow. It's similar for the optimized local mesh that I will talk about, but the main workflow is based initially in the terrain elevation. So I'm using for this example a terrain elevation of an hypothetical pipeline. It's not a real one, it's just one that I use for demonstration only. And the terrain is obtained from the USGS website that is indicated here. This is south of the city of Seattle in Washington State in the United States. And what I'm assuming here is that there is a pipeline that is on the south of this valley here. So the pipeline is this one over here. This is a detail of the pipeline already with the spills generated. You can see a detail here, but the way to generate that is to, once you have the pipeline enter into the model, you use the run oil pipeline break model within the OilFlow2D system. Then you enter the parameters, the calculation interval. In this case, we're using 1 second. It's recommended to use small value here for greater accuracy. You enter the distance between the spill points, in this case 100 meters for the example. The leak diameter, so this is the diameter of each spill location. Discharge coefficient, this is a coefficient that is used to determine the outflow from the orifice, and is based on the orifice hydraulics. The friction coefficient of the pipeline, the density of the fluid, kinematic viscosity, and you can select here whether to use the basic model or the heat transfer oil spill model for the overland spill. This is the initial pressure head of the pipeline at the end of the pipeline. This is the pressure head at that location. The initial flow rate for the pipeline, in this case is cubic meter per second in metric units. The valve closing time, we're assuming that the valves will close instantaneously. And then you can select here the DEM layer to assign the elevations to the spill points. We have added new functionality recently, either to create elevations from multiple DM boundaries, and mainly the use of local mesh. As if you are familiar with the previous versions, you were required to generate a mesh that would cover the complete set of spill points. This is no longer required. It's still an option, but it's no longer required, as you will see in the next few slides. When using the local mesh, you can select the cell size for each local mesh, and also the initial size of the domain around each spill. So once you do that, you will have each of the spills located according to the spacing that you have selected. And the sources layer is also pointing, each point is pointing to the hydrograph that the model has calculated along the pipeline. You can see here another detail of the pipeline and the spill locations. Now, the way the oil leak discharge calculation works starts by calculating the initial steady state. So along the pipeline, this would be the pipeline profile. And we calculate based on the pressure head at the end and the initial discharge of the pipeline, we calculate the total energy line or the total energy at each spill or at each location along the pipeline before the spills have occurred. So we have the discharge and the pressure along the pipeline. This is very important because the initial pressurization of the pipeline will determine in a big way how much oil will get spilled, because it's not only gravity that is playing a role here, it's also the pressure on the pipeline that affects the outflow. So this is a typical profile of a pipeline. And then for each spill location, let's say this is a spill location, we determine how the drain down occurs in these two stages. The first stage, before the valves are closed, when the pipeline is pressurized, and then the second stage when the pipeline is being depressurized based on the location of the spill point. So this graph represents how this is schematically represented. Of course, the computation is much more complex because we apply the continuity equation for the pipeline for the points from the left to the spill location and from the right to the spill location. And these locations are based not only on the highest point on each side, but also because the initial flow can occur due to the pressurization from farther away, even if it's lower than the highest point here. That's why the volumetric computation is not accurate for this kind of computations. So we apply the continuity equation and also the energy equation to compute the outflow from here. And as the flow is being drained in here, there may be areas where the fluid will remain on the pipeline and some other areas that will drain down as well. So once we compute all that, there's a number of results are generated for each spill. So the spill discharge for each time and along the drain down period. So once we have that, then we can start the batch run for all spills. And this batch run process is the one that will automate the running of thousands of spills. Now it can, it requires little user interactions, as we will show, and the results of each spills are written in separate directories. So the model organizes everything in different directories. Each will represent a single spill. Now the new development involves the process of what we call the local mesh optimization. In the local mesh optimization, we are no longer required to have a single global mesh for the whole set of spills as it was before. So before we had to develop a single mesh covering everything that was usually very big. This is no longer required. So the model now will generate local meshes automatically for each spill. The thing is that these initial local meshes may be not sufficient to contain all the spills. So the spill will hit that mesh at the boundaries, and that means that the mesh was not big enough to represent what happened in a real situation. So what happens in the model is that the oil detects that the model detects that the oil impacts the boundary of that mesh, and then extends it to farther away so that it can perform a new computation, and then it continues expanding until all of the spills are contained in their respective domains. So the advantage of this process is that it requires minimum user intervention. The global mesh is not required, and consequently, you will have much smaller meshes with increased local resolution, shorter run times, smaller file sizes, and shorter map generation times. So it's all advantages for this new process. So in the past, when you had a number of spills, as you have in this particular example, you were required to have the global mesh. And then it was a real simulation that had a mesh of 2.7 million cells. Now, what is the problem with that, or what was the problem with that, is that that mesh needs to be copied to each of the spills, because each spill would use the same mesh, the whole mesh, even if the spill is very small, as in this case. You can see here, one single spill only impacts a few cells very close to it here, but still needed the whole mesh, which generated a lot of overhead that it was not necessary. Now, what we're doing now, instead of using the global mesh, we use a local mesh that is only applicable to each of its spills. This local mesh is much smaller, as you can see here. Now with a 70,000 cell mesh, we have enough cells to contain the flow here. This is an animation of the process of how it works in practice. So you see here, initially there is a computation of the spill. It hits the boundary, and then it repeats the computation with a larger mesh. It still hit the boundary, and it expanded further away automatically. This is all an automatic process until it's contained, as you can see here in the last part. So with the 3 loops, the model was able to generate automatically the final mesh extent that required for the computation. So if we go backward here a little bit, you can see here, this is the almost final stage of the final mesh that was able to contain the complete flow of this particular spill. So the process is totally automated. So there is no need, you don't need to create a mesh. You don't need to worry if the mesh is going to cover the whole spill area. So each spill will take advantage of the information you have in the terrain, and then it will expand the domain according to what it needs to be able to contain the whole fluid here. So once you have that, then the model will allow you to generate the maps, and with the maps you can have still the same offer of different maps for depth, area affected, spill times, arrival times, and so forth. It's the thing is that with the local mesh, you get the extra advantage of the speed. So in the past, it was very slow, but now it's with the local mesh is much faster. So this is a table that I prepare with a specific example of the previous mesh that I show you, where the number of cells that was required was 2.7 million. And on top of that, this mesh was required to be developed by the user. So you need to develop that mesh and make sure that that mesh was far enough from the spill location so that it will cover all of the fluid once the spill occurred. Now the local meshes take only require only 67,000 cells for typical spills. Now runtime, it's a big thing because in the past with this big mesh and the number of spills, in this case 81 spills, it required 8 hours of computing time. Now it takes only 1.5 hours with the local meshes. Project size is reduced from 1.39 terabytes to 36 gigabytes. So you can imagine how difficult it was in the past to do real cases or long pipelines, because you need a huge amount of hard drive space to accommodate this kind of spills. Now with 36 gigabytes, it makes it much easier to have multiple scenarios. The map processing time is also being reduced, as you can see here, considerably. For this particular case, generating a area of inundation maps and spill arrival times, it took about 4 hours, and now it takes about 3 minutes. So it's huge difference and huge optimization in all of these aspects. So this new development is going to be distributed to all of our current users of the oil pipeline module, and it's going to be distributed initially in beta version for testing, probably by the end of this week. And any further information, you can find it in our website, and also by writing to our email, or my personal email if you want, is rey@hydronia.com. So thank you very much for your time and interest. And if you have any question, I can accommodate a couple of questions now. So let me see if there is any question here. Yeah, I have a question about the. So the question is about the interface of the oil pipeline with the overland flow. So is the oil pipeline module automatically connected to the overland flow? Well, automatically in the sense that, so the workflow is as follows. You first enter the pipeline with the terrain, and then run the pipeline module, and that will compute the outflow from each spill location. Then you export those files to the model, the overland flow model, and then it will read automatically those files. So in that sense, it's connected. So because there are some users that would be interested only in the determination of the flow rate coming out of the pipeline, and you can do that independently. But then if you want to do the overland, then you run the overland. Now, with this new optimization, it's much seamless the integration because you don't need to develop the mesh yourself. The mesh will, the model will take care of that for you. Okay, when is going to be this available? It's going to be available in beta, as I mentioned, in later this week, and probably a couple of weeks more will be formally included in the distribution. Okay. Okay. What about the other question I have is about the integration of the overland flow with the water flow. Well, we are actively working on that integration now in two forms. One is the what we call the more detailed or the detailed computation, and the second one is the simplified. Now, the detail involves the use of the overland flow to a, let's say the flow gets to a water body, and then the integration will be automatic in the sense that if you have previously computed the flow within the water body, the flow of the oil will continue on the water body and being transported according to the hydrodynamics previously computed. So that is the full model itself, or the detailed model. The second one, which we are going to be working on based on the requests from several users, is a simplified one in which we will take advantage of some databases or some layers that include the stream channel information for a given location, and this stream channel in some locations contain the some hydraulic parameters, very simplified hydraulic parameters such as velocities, flow direction, discharge of water, and so forth. And based on that and the computations of the model will determine if there is a hit to that stream, particular stream, and then with the layer information about the stream velocity and so forth, it will transfer the volume that hits the water body downstream. So it's very simplified, but it's sometimes enough for some users that require just the areas that are affected and how far the oil gets to different locations. Well, I think that I have completed the time that I had allocated for this. So if you have further questions in the future, feel free to email me at the email that appears here. And if you are interested, we have further information on our website. So thank you very much for your time and interest, and I'll see you in a future webinar. Thank you very much.